regenerative cycle, the steam enters the turbine at 30 bar, 400 degrees centigrade, which is obviously the superheated steam, because once the pressure and temperature are given, it can be said that the steam should have been a superheated steam. So, and the exhaust pressure, obviously the condenser pressure, is 0.10 bar. The feed water heater is a direct contact type which operates at 5 bar. This 5 bar should be the bleeding pressure of steam. Find A, the efficiency and the steam rate of the cycle, and B, the increase in mean temperature of heat addition efficiency and steam rate as compared to Rankine cycle without regeneration. Neglect pump work. Pump work can be neglected. The solution to this problem could be given like this. First of all, let us define what do you mean by steam rate. Steam rate is defined as the mass of steam to be circulated in the cycle in kg to produce 1 kilowatt hour or 3600 kilojoules of work output. Now the steam rate units are kg per kilowatt hour. Steam rate can be calculated as 3600 divided by net work output in kilojoule per kg. Now let us draw the cycle on temperature entropy diagram and give the salient points. Now there are three pressures in the problem. They are 30 bar boiler pressure, and the inlet temperature of the steam to the turbine is 400 degrees centigrade. There is a bleeding pressure of 5 bar, and there is a condenser pressure of 0.1 bar. Boiler pressure is BP, condenser pressure is CP. In between we have the bleeding pressure at 5 bar. There are 7 salient points. Neglecting pump work, H7 can be taken as H6 and H5 can be taken as H4 neglecting pump work. Now let us calculate first of all what is H2. Now problem is to get H2. To get H2 we need dryness fraction of steam at state 2, for which we have to equate the entropies. S1 is superheated entropy at 30 bar, 400 degrees centigrade is equal to S2 is SF plus X2 into SFG at bleeding pressure of 5 bar. Now S1 is given from the tables as 6.921 kilojoule per kg Kelvin, which is equal to S2 is equal to S3, because 1 to 3 is isoentropic expansion of the steam. SG at 5 bar is given from the table as 6.8213 kilojoule per kg Kelvin. Since S2 is greater than SG at 5 bar, state 2 must lie in the superheated region. From superheated steam tables, the temperature corresponding to T2 is 172 degrees centigrade and H2 is equal to 2796 kilojoule per kg, because state 2 is a superheated steam. So now to get X3, S1 is equal to S3, which is equal to, what is S3? SF plus X3 into SFG at P3. That is, what is the pressure at 3? Condenser pressure given as 0.1 bar, implies 6.9212 is equal to 0.6493 plus X3 into 7.5009, from which the dryness fraction after isoentropic expansion at condenser pressure is calculated as 0.836, from which enthalpy at condenser pressure at 0.1 bar is HF plus X3 into HFG at 0.1 bar condenser pressure, that is 191.83, which were obtained from the tables, into 0.836, which is calculated earlier, into 2392.8 kilojoule per kg. So the answer for H3 is 2192.2 kilojoule per kg. Pump work is neglected. Therefore, H4 is equal to H5 is equal to 191.83 kilojoule per kg. H6 is equal to H7 is equal to HF at 5 bar. This is equal to 640.23 kilojoule per kg. So energy balance or heat balance for feed water heater gives M, the mass of steam bled, into H2 minus H6 is equal to 1 minus M into H6 minus H5. H5 is H4 already, we know that, from which M can be calculated as 0.203 kg of steam bled per 1 kg of steam entering turbine from the boiler. For 1 kg of steam entering the turbine from boiler, we had calculated mass of steam bled from the turbine.
Now, work output of the turbine can be calculated as enthalpy drop of steam before bleeding per 1 kg of steam plus after bleeding the work done in the turbine is 1 minus m into H2 minus H3, that is 3230.9, that is H soup at 30 bar and 400 degrees centigrade, minus H2 is obtained as 2796 kilojoule per kg plus 0.797, the steam left after bleeding in the turbine, into 2796 minus 2192.2. This gives 916.13 kilojoule per kg. That is a net work output of the turbine. Heat supplied in the boiler per kg of steam, that is H1 minus H6. This is calculated as 2590.67 kilojoule per kg. Therefore, thermal efficiency of the regenerative Rankine cycle, neglecting pump work, is net work output of the turbine divided by heat supplied in the boiler. This results in 35.36%. Steam rate can be calculated as 3600 divided by net work output of the turbine. This gives a 3.93 kg of steam to produce 1 kilowatt hour of work. The mean temperature of heat addition is enthalpy change in the boiler per kg, that is heat supplied, divided by entropy change, that is the mean temperature of heat addition. This gives 2590.67, that is H1 minus H7 divided by 6.9212 minus 1.86. This results in 511.95 Kelvin. This is the mean temperature of heat addition, which is equivalent to the 238.8 degrees Celsius after subtracting 273. Mean temperature of heat addition, if we calculate without providing any regeneration, please note that this is H1 minus H4 divided by S1 minus S4. This results in 39.07 divided by 6.9212 minus 0.6493, that is S4 value, which results in 484.55 Kelvin, which is equal to 211.4 degrees centigrade. Clearly we can note that there is an increase in mean temperature of heat addition due to regeneration, because of which thermal efficiency is increasing. Work of turbine without regeneration is H1 minus H3. If there is a direct expansion without regeneration, kilojoule per kg, it is obtained as 1038.7 kilojoule per kg. Therefore, also steam rate without regeneration is equal to 3600 divided by 1038.7, that is work output per kg. This is obtained as 3.46 kg per kilowatt hour, and thermal efficiency of this cycle without regeneration is equal to
H1 minus H3 by H1 minus H4, that is net work output of the turbine divided by heat supplied, neglecting pump work, that is 1038.7 divided by 3039.07. This obtained as 34.18%. Clearly, there is increase in the thermal efficiency due to regeneration. With regeneration, we got the thermal efficiency as 35.36. Without regeneration, we got the thermal efficiency as 34.18. And if you look at the work outputs there, work of the turbine with regeneration is 916.13. Without regeneration is 1038. This decrease in work output with regeneration is due to the reason that there is around 20% of the steam is bled. For 1 kg of the steam entering the turbine, there is 0.2 kg of steam is bled from the turbine. That is the reason why total work output of the turbine after regeneration per kg of steam entering the turbine is reduced. For 1 kg of the steam entering the turbine, the work obtained when regeneration provided is reduced, because work output is reduced because there is certain amount of the mass of the steam is bled from the turbine. So that is the reason why with regeneration we got 916.13 and without regeneration we got 1038 kilojoule per kg. Now I shall consider the increase in thermal efficiency of Rankine cycle by providing higher degree of superheat without changing boiler pressure BP and condenser pressure CP. We see this method now on temperature entropy diagram. This is the simple Rankine cycle I had considered with a degree of superheat provided. Now, if we supply the steam at a higher temperatures without changing the boiler pressure, the expansion would be considered like this: 1 dash to 2 dash. 1 to 2 is expansion, isoentropic expansion of the steam with a lesser degree of superheat. With the higher degree of superheat, the expansion of steam in the turbine is shown with 1 dash to 2 dash. With higher superheat temperatures are provided at the inlet of turbine, higher thermal efficiency of the cycle is obtained because with higher degree of superheat the mean temperature of heat addition is increased. When mean temperature of heat addition is increased, obviously we can expect more thermal efficiency. That is, I can say between 4 to 1, if there is lesser mean temperature of heat addition is there, between 4 to 1 dash there is a higher mean temperature of heat addition is expected. Obviously thermal efficiency of the cycle will increase when higher superheat temperatures at the inlet of the turbine are provided. But nowadays the maximum temperature, that is allowable temperature, could be expected not more than 500 degrees centigrade. So I can say the maximum temperatures of the steam supply nowadays employed in India in the steam power plants is around 500 degrees centigrade, not more than that. Also, another benefit of providing higher superheat temperatures for the steam at the inlet of the turbine is the turbine is subjected to lesser moisture contents, because x2 dash is greater than x2, there is a lesser chances of turbine blade erosion. So apart from increasing thermal efficiency, another benefit we get from providing more superheat temperatures of steam at the turbine inlet is turbine is subjected to lesser moisture during later stages of expansion. There is lesser chances of turbine blade erosion. Now let us consider another objective question regarding the Rankine cycle. In a Rankine cycle, if the exhaust pressure of the turbine is increased, the quality of steam leaving the turbine A does not get affected, B increases, C decreases, D cannot be predicted. If we draw the cycle on temperature entropy diagram, if this is the simple Rankine cycle, the exhaust pressure is increased. The exhaust pressure means the condenser pressure is increased, which means the quality of the steam will increase. Answer is B. So higher condenser pressures means higher dryness fraction values. But this may be advantageous in one way, because turbine blade erosion is reduced. But when higher condenser pressures are employed, turbine work output will get reduced. Now there is another objective question is taken regarding the Rankine cycle. In the reheat modification of the Rankine cycle, A, the efficiency is increased by increasing the average temperature at which energy is added as heat. B, the efficiency is increased by decreasing the average temperature of heat rejection, that is condensing temperature,
See, the moisture content is high in a low pressure region of the turbine. D. The moisture content is low in the low pressure region of turbine. The question can be answered by looking at the TS plane of the TS diagram of the reheat Rankine cycle. Two to three is isobaric reheating. So if there is no reheating, the steam would have expanded as shown in the dotted line. That means steam is having lesser dryness fraction values or more high moisture content, whereas 0.4 dash is the state of the steam obtained after reheating is provided during later stages of expansion. Therefore, answer is D. The moisture content is low. X4 is greater than X4 dash. 4 dash is the state of the steam after direct expansion without reheating, whereas state 4 is the state of the steam when reheating is provided, that is during the latter stages of expansion. So answer is D. And looking at the option A, the efficiency is increased by increasing the average temperature at which heat is added. When the reheating is provided, the mean temperature of heat addition also would increase. Therefore, efficiency may be slightly increased. Answer is also A. There are two answers for this question, because when reheating is provided, there is every possibility that mean temperature of heat addition would increase, because of which thermal efficiency of the Rankine cycle shall increase. Now there is another problem given on the steam power plant or thermal power plant working on Rankine cycle. The problem is given like this. In a thermal power plant, superheated steam at 2.5 megapascal and 250 degrees centigrade enters a turbine. The plant engineer would like to study the effect of condenser pressure on the performance of the power plant. Calculate the thermal efficiency and the quality of the exhaust steam if the condenser is maintained at 10 kilopascal and 5 kilopascal. The solution to this problem could be given like this by indicating the cycle, simple Rankine cycle on TS plane. Now we are employing two different condenser pressures, keeping the boiler pressure same. This is the Rankine cycle with higher boiler pressures, namely 10 kilopascal. Boiler pressure is same, that is 2.5 megapascal. In this problem, boiler pressure is not changed. We are only decreasing the condenser pressure. Now let us indicate the with a lesser condenser pressures, that is 5 kilopascal. So 1, 2, 3, 4, 5 is a cycle with lesser condenser pressures. 6, 7, 3, 4, 8 is a cycle with higher condenser pressures. Now let us consider the condenser pressure of 10 kilopascal. At 2.5 megapascal and 250 degrees centigrade, H4 is equal to 2880.1 kilojoule per kg. This is the enthalpy of steam at turbine inlet, and S4 is 6.4085 kilojoule per kg Kelvin. For steam at 10 kilopascal, from the saturated steam properties, Vf is given as 0.00101 meter cube per kg. Hf is 191.83 kilojoule per kg. Hfg is 2392.8 kilojoule per kg. Sf is 0.6493 kilojoule per kg Kelvin. SFG is 7.5 kilojoule per kg Kelvin. Now enthalpy at H1, H6 is 191.83 kilojoule per kg. Therefore, from which equating the dryness fraction values, S4 is S8, we can obtain the dryness fraction values X8 as 0.7678, implies H8 can be obtained as 2029.02 kilojoule per kg. Work of pump is integral VdP, that is specific volume of the water, into boiler pressure minus condenser pressure, which is obtained as 2.51 kilojoule per kg. H7 is H6 plus pump work, which is obtained as 194.34 kilojoule per kg. Therefore, thermal efficiency with 10 kilopascal condenser pressure is H4 minus H8 minus H7 minus H6, that is pump work, divided by H4 minus H7. It is obtained as 31.6%. Now, having seen the thermal efficiency of the Rankine cycle with the condenser pressure of 10 kilopascal, now let us do the problem of the Rankine cycle with the condenser pressure of 5 kilopascal with using the same boiler pressure of 2.5 megapascal. Steam properties at 5 kilopascal are given as Vf is 0.001 meter cube per kg, that is the specific volume of water. Hf is H1 in the cycle, that is 137.82 kilojoule per kg. HFG is 23.7 kilojoule per kg. SF is 0.4764 kilojoule per kg Kelvin. SFG is 7.918 kilojoule per kg Kelvin. Equating S4 is equal to S5, we get S4, that is entropy at 2.5 megapascal, 250 degrees centigrade is equal to SF plus X5 into SFG at 5 kilopascal. Equating the entropies, we get the dryness fraction as 0.7491 at state 5. You see, if you look at that, dryness fraction values are getting reduced with the lesser condenser pressures. Dryness fraction values of steam when lower condenser pressures are employed are lesser during latter stages of expansion. You can see here X5 is lesser than X8, which means more chances of turbine blade erosion. Now let us calculate H5 as 137.82 plus 0.7491 into 2423.7. We get H5 as 1953.4 kilojoule per kg. H2 minus H1, that is pump work, is equal to integral VDP, that is 0.001 into 2.5 into 10 cube minus 5, that is 2.51 kilojoule per kg pump work is required. Therefore H2 is equal to 137.82 plus 2.51, that is H1 plus pump work, that is 140.33 kilojoule per kg. Therefore thermal efficiency of the cycle with the condenser pressure of 5 kilopascal is equal to, looking at the cycle, that is H4 minus H5 turbine work minus pump work
that is H2 minus H1 divided by heat supplied in the boiler. Substituting the values, we get thermal efficiency as 0.337, that is 33.7%, whereas with the 10 kilopascal condenser pressure we got 31.6%. So the conclusion here is, when lower condenser pressures are employed with the boiling pressure constant, we are likely to get more thermal efficiencies at lower condenser pressures. But simultaneously, there is a danger of turbine blade erosion when lower condenser pressures are employed, even though we get more thermal efficiencies at lower condenser pressures. Now, let us consider another objective question regarding the Rankine cycle. The thermal efficiency of an ideal Rankine cycle is lower than that of a Carnot cycle operating between the same temperature levels, because A, energy addition does not take place at constant temperature. B, energy rejection does not take place at constant temperature. C, the turbine is not reversible and adiabatic. D, the pump is not reversible and adiabatic. Now, the answer to this question could be given if you look at both the cycles on TS plane when operating between the same temperature limits. Carnot cycle is a rectangle on TS plane. A, B, C, D is Carnot. If you draw between the same temperature limits, if you draw the Rankine cycle, A, B, C, D, E, F. A, B, C, D, E, F is ideal Rankine. Ideal Rankine. Please mind that there are no irreversible differences in the cycle. A, B, C, D is Carnot. Definitely, thermal efficiency of the Carnot is thermal efficiency of ideal Rankine. The reason is energy addition does not take place at constant temperature. In the Carnot cycle, the heat addition occurs at A to B only, whereas in the Rankine cycle, heat addition occurs at between F and B. Between F and B is the heat addition in the Rankine cycle. That is the reason. A is the answer. But in both the cycles, heat rejection occur at constant temperature. In both Carnot and Rankine cycles, ideal Rankine cycles, heat rejection occur at constant temperature, as we have seen in the figure. C to E is the heat rejection in the Rankine cycle, whereas CD is the heat rejection in the Carnot cycle.